All right, so let's go ahead and get started. So yesterday, or rather on Monday, we talked about basically, direct proofs, but more so than that, I kind of introduced a method in which we should think about writing mathematics, and a method by which we do proofs. And it's not so much, like I'm sure I've beating this dead horse right now, but essentially I want to be able to show you guys all these different techniques, right, in standard ways in which to prove things, but I don't want these techniques to be kind of the only things you have, right? I don't want you guys to feel like, oh, if I see this type of proof, I have to do it this way. Because at the end of the day, these techniques are only there as guidance, right? They're only there to help you see like what you should do, or if I'm stuck, what are some things I can try. And you'll see this more and more as we go on in the course, right? As we start talking about multiple different types of proofs, different types of problems, you'll kind of see that there is a standard way to do it, but it's not necessarily the only way to do it, right? That's part of what I'm going to talk about today. So, I'm going to finish up with direct proofs, and we'll go on to proofs by contradiction and proofs by the contrapositive, and we'll kind of see how we can apply each of those to like the same problems, right? And sometimes it might even be that they're harder, right? They might be about the same difficulty, it's just whatever you find more natural, right? So before I dive into that, I realized there's a few more things I want to say about mathematical writing, right? So, when most people say mathematical writing, at the undergraduate and graduate level, this really just means your proof writing, right? This is really just referring to, as you write your proofs, what are some things you should take note of? As you start going towards a research level, you'll start having to write actual papers, and that's just, the typical, how do you write English, right? How do you write English, how do you string things together to make it sound like a nice paper? But a lot of that comes almost naturally, right? Or if it's either it comes naturally or it doesn't. And if it doesn't come naturally, it's one of those things you kind of have to work at, but that's less on the math side of it and more on the writing side. But that is still a skill that is good to have as a researcher, right? There's tons of papers out there that have brilliant mathematics in them, but it's really hard to read the paper because the writing is just so convoluted, right? There's a paper I read this past semester for one of my seminars, and it was this like 150, 160 page paper that just had a bunch of notation and introduction to these techniques for some process. And the mathematics were fine, but it was just incredibly hard to read because it was just so convoluted, and there was no organizational structure, there was no like flow to it, and that's kind of what I want you guys to avoid, and it's part of what we're going to kind of put into this class, right? So as we go through and as I kind of introduce you to mathematical writing techniques and mathematical proof techniques, I want you to kind of use that in the future and kind of see, okay, if I'm reading a book, how should I want it to flow, right? It should flow kind of like proofs here. And then in that case, when you eventually if you eventually write a paper in math, you kind of want to read through it and go, okay, if I was someone who didn't write this paper, if I was an author, if I was just someone who maybe didn't even know anything about this field, can I still read through this paper and get something out of it, right? A lot of people seem to have this idea that, papers are hard, right? A lot of mathematical papers are hard to get into. And it's very rare to just read a paper from start to end and be like, okay, got everything in, cool, right? That's pretty rare. But at the same time, there shouldn't be this barrier where, oh, if I read this paper and I'm not in this field, like let's say I'm reading something abstract algebra, it shouldn't be the case where I feel like I can't read the paper if I'm not an abstract algebra. Even if I'm an analysis of something else, I should still be able to have enough knowledge to figure out what I need to know as background to read the paper and then get something out of the paper. And that's what I want you guys to start incorporating in your proofs, right? Obviously, these aren't like super big results or anything. They're just you're proving for homework or as an exercise. But still, I want you guys to write it as if the reader of your proof is someone who knows just logic, right? They know how to think about logic, they know how to think about mathematics, but they might not know what you're writing, right? But you want to write it in a way that makes sense. So to kind of help with that, let's come up with a few like base rules that we should keep in mind. And the first one is, this is more a typographical thing, but it does help, right? And I'm gonna ignore the obvious case of writing full sentences, right? The same things you've seen in English classes, right? Don't start a sentence because, don't have a sentence be its own sentence. Do all of those things, right? Write in full sentences, because this should read as if it was a paper. This should read as if it was an English paper, where you just explain something, right? But first of all, we want to start sentences with a word and not a symbol, right? Or any sort of mathematical symbol. Why is this? Well, it's just for clarity, right? If I write A and B are sets, this can get kind of ambiguous. Sorry, maybe that's the wrong word. This is not, I might not say ambiguous, but I might start reading this and I think, oh, this is the word A something, and then go, oh, A, and then I just change my thinking to, oh, right, A is a symbol. I should think of it as a symbol, right? Instead, if this is capital, there's no disambiguity or no having to check this, right? I start with the word let, and this is why I personally start a lot of my proofs with the word let, because when I use let, I know that the next thing coming out is going to be a symbol probably, right? It's going to be some mathematical object. In this case, it's a set, right? I know that this is not some capital letter because it's at the start of the sentence, right? Another example is if I want to write an equation, I want to write something like, oh, x squared plus 2x equals 7 or something like that. Don't start with that. And moreover, obviously don't be like, oh, I should start a sentence with a capital letter, so don't do that, right? Start with the word let, right? Let this be equal to 7, or suppose this is equal to 7, right? If you want to use suppose, that's fine, because you're not letting this be true, you're assuming this to be true. You can change up your words like that, you can change up the word you're using, but that's fine, as long as you start with a word. Right, so avoid starting your sentence with a mathematical symbol. Just start it with a word. That way, it's completely unambiguous where the symbols are. Right, I don't have to think about whether the first word is the symbol or a word. I just make it really obvious that it's a word. That's the problem there. The second thing is use connected lists. And what do I mean by that? I mean words like since, therefore, hence, because, etc. Right. And I give you a whole bunch because there's obviously a lot more synonyms. There's many more things you can do here. Or you can even use phrases like, it turns out that something. Right, or we have that. Right. And what this does is it tells your reader that you're going through, and at some point you're saying, yes, this next statement I'm about to say is because of this previous statement, right? You want to make that correlation and causation very, very clear, right? So if I write something like this, you can see how grammatically this is not wrong, since x equals 7, 2x equals 14, right? It's because of this that this is true. But notice how the comma can make it confusing, right? Am I saying since this, then this is true? Or am I saying since these two are both true together? What am I trying to say? So don't say this. Say something like, since x equals 7, we must have that 2x equals 14, or something like that, right? Or you can say 2x equals 14 because x equals 7. Generally, people will avoid using that because that way, because you're kind of flipping the direction. And so since the implication is sort of going left to right, you want to write it in a way that keeps it left to right, right? Maybe we know, another way you can say this is we know x equals 7, therefore 2x equals 14. And again, x equals 7 technically is a statement on its own, but I'll start this with English words because then we don't have any disambiguity at all. So we know x equals 7, therefore 2x equals 14. And now it's very unambiguous as to what I mean. I mean that we start with a statement of x equals 7, and because of this statement, I then have this other statement, right? So this is something really important that you guys should learn, because I read a lot of mathematical proofs from students, and they're very, I mean, they're correct, but they're very discombobulated, right? I just see a bunch of phrases stuck on the page, and people would just write this, then this, then this. Sometimes there's just commas in between, sometimes there's no explanation, and it's very hard to read, right? Doing something like this will avoid that. You will find differing opinions amongst professors and amongst people who do mathematics, but my opinion is use as many words as possible to describe what you mean and what you want to say, right? And I don't mean use words instead of symbols. I don't mean like find places where instead of symbols you can use words and make your proof look longer. That's all I mean. I mean, whenever you have a chance to make something more clear, take that chance, right? If you're reading through a proof and you're like, well, there's like a 1% chance that someone's gonna like misunderstand or misconstrue this, don't take that 1% chance, right? Just make, if there's any possibility of it being unclear, make it more clear, right? And this is good for you as well, because sometimes if you think something could be unclear and you say, okay, I'm gonna rewrite it, and in the process of rewriting it, you start getting jumbled up. Well, maybe that's a sign that you need to kind of think about your argument, right? Because if you know what your argument is, converting it into something like this should be really easy. You should already have a flow in your head of how the argument goes, and then if you need to make it more clear, you can just be, you can just specify. But if you're having problems making it more clear, maybe you need to revisit your argument and see if there's something you need to rework, right? See if there's something that you're not quite understanding, that you think you understand, and delve into that a bit further. But these are the two big things I want to mention about mathematical writing. Now there's a lot of them, right? So some people are always very specific about end every sentence with a period just to make sure that it's clear. Well, that's an obvious thing, right? We've all known since grade school, like end your sentence with a period. But like the case comes in where you're writing something in LaTeX, maybe something that looks like this, right? So something will have text, and so we have, and I'll put a colon here, and then I'll write some mathematical symbol like in the middle, right? So let's say here's our page, and here's our text. I'll have something like, oh, x equals 7, and like in the middle of the page, right? You've seen this a lot. Well, the idea is if this is the end of your sentence, put a period there, right? That way, you know that what you're writing next is its own sentence. I personally forget this a lot. I don't usually put periods or commas at the end of my equations, just because I tend to write my papers in a way that if I am putting something as an equation, it is the last thing in that sentence, and it's very clear that it is. And then the next segment starts its own paragraph, right? That's my personal choice, but it is good to have a very clear end of sentence here, right? So it might seem stupid to hear people say, oh, end of sentence with period, but there are cases where it's like not quite clear whether you should or not, right? So that's kind of one of those things. There are some books that will talk more about mathematical writing and all these things, but these are the two big ones that I think you guys should put it on. A couple of you have turned in homework assignments 1 and 2, and I gave some feedback on each of them. Just note that a lot of my feedback will include stuff like this. Even if you have a proof that's completely correct, and I'll give you full marks for it, I might still make notes of, okay, let's maybe write this a different way to make it more clear, or let's change the way in which you word this because it's possible to misconstrue. I'll try to make sure to be clear about cases like that where you could improve your writing a little bit, right? And that's part of what this course is for. I'm not gonna write it on the board, but I said this a little while back on like day 1 or something like that. Don't use the word it, right? Because sometimes it's very hard to know what it refers to, especially if you have a long proof, right? So maybe I'll give you an example of this. Let's see. Since x is a subset of y and x is not empty, right? It is not empty. Right, this can be a bit weird, right? What is it referring to? Is it referring to x, in which case I already said that. Is it just trying to clarify the symbol or what, right? We will want to say something like y is not empty, right? Something like that. So avoid using the word it. This is one of the things I will be very, very strict about in the homework, right? I might not take points off for it unless you do it a lot, but I will always circle the word it and use it and say, okay, what is this referring to, right? If it's referring to something, of course, right? Like if you're saying a statement like it is obvious that blah blah, that's completely fine, right? It's just don't use the word it to refer to something else when you can just use that symbol, right? Don't be lazy. It doesn't really save that much time to actually point out what you're referring to. Okay. So let's just go on with direct proofs. So last time we talked about having a conditional statement. If we have something like P implies Q, we can just start with assuming P and coming up with Q. Let me give you a couple more definitions, and then we will look at another example of a direct proof, and then we'll talk about a proof by cases. So more definitions. So far, we have definitions for even, and we have definitions for odd, right? I'm not going to write this as a definition, but if you ever hear the terms parity, right? If two things have the same parity or different parity or opposite parity or whatever, parity just refers to the evenness or oddness, right? So it's a way of just making it easier, right? If I want to say two numbers have the same parity, I mean that either they're both even or they're both odd, right? And it's just a way of avoiding that, right? I don't want to just have a case where they're only both even or only both odd. I want to refer to both of them at the same time. I call it pair, right? And the word pair is just because things are either even or odd, right? So maybe we can have a proposition. If a number is not even, then it is odd. Oh, sorry, if an integer is not even, then it's odd. And same thing vice versa, right? If these two things directly contradict each other, and every integer is either even or odd. But these are propositions. You can prove this using the definition. So what are some other definitions? So that's A, B, say A divided B. So this symbol here, this bar, is just divides. And we remember, this is not divisible by, this is exactly divides. And you don't want to think of this as the same version as the division sign, right? This is not the division sign. In fact, this is almost the opposite, right? I'm hoping that you guys aren't hearing the construction outside. It's noisy. So A divides B. There exists a K in the integers such that B equals to AK. Right? Notice that I didn't use division, right? I didn't divide it. I'm kind of defining divides as a word using multiplication, right? You can think of this as A divides into B or A goes into B, right? As some of you might have heard that term before, but this is what we mean by definition, right? So you'll either see this symbol or this symbol, or this phrase rather, for B equals to AK, right? So example, prove that 2 divides 4, right? Here's my A and here's my B. Well, my proof starts with let K equals to 2, which is an integer, right? 4 equals to 2 times 2, so 2 divides 4, right? Just by definition, right? And obviously, when we're proving things just from a definition, usually it's pretty quick, right? It's just a one-step thing. But this is what it means to divide, right? It's not that we're taking 2 and dividing it by 4. We're saying that 2 goes to the 4. And I don't need to say how many times. I don't need to say that 2 goes to the 4 2 times. I'm just saying that 2 goes to the 4. That's it. Right? So that's what it means to divide, right? There's a couple other definitions we do. You guys have heard this a lot. You guys have maybe used it in high school or before, but now we're going to formally define it. We're going to let A and B be integers again. Oh, and by the way, I should note that keep in mind that when we talk about even and odd, and even in here, and also in here, for dividing, notice these are all integers, right? I never said positive integer. So these include negatives, right? Negative numbers can be even, negative numbers can be odd. Sorry, negative integers can be even or odd, right? I didn't restrict this to saying like, oh, positive integers. So everything I'm talking about here refers to just all integers, right? This is why I use Z and not the natural number n. So that is something to keep in mind. This definition works equally for, what's it called? Equally for positive and negative integers. I guess I should include a couple other terminology, pieces of terminology here. If A divides B, then we say B is a multiple of A, or A is a divisor. Right, and this is stuff you're used to, right? This is not something you've not seen before. If I ask you what's a multiple of 2, you'd be able to tell me. If I ask you what's a divisor of 8, you'd be able to tell me. This is just a more formal way of looking at it, right? And this extends it to the negatives as well. -5 is a divisor of 5, right? And then -10 is a multiple of 2. Even though it doesn't make sense, you think multiples are typically going upwards, but that's only because we normally work in just a positive integers. But in this case, we include negative integers. Okay, so going into this next definition, right? We can talk about the greatest common divisor. So the greatest common divisor of A and B, also denoted as GCD, so a lot of times you'll see this notation, GCD parentheses A comma B, right, where it's almost like this is your predicate and this is your argument, right, and it spits back, not a true false, but it spits back a value, and this is a formula. GCD A and B is the greatest common divisor of A and B. This is an integer following certain properties. So I'll call it D, right? And let's define it a certain way. We'll say that D is a divisor, right? So D divides A and D divides B. That's our definition of being a divisor, right? So the greatest common divisor of A and B should obviously be a divisor of A and B. Right, and then here's a weird definition, right? So this is what I'm about to give is the standard definition for the greatest common divisor, and I'll talk more about it in a bit, why there might be an equivalent definition you're more used to, but this is more proper, right? So for all C in the integers, where C divides A and C divides B, we have D divides, right? C divides D. So this is weird because when I think greatest common divisor, I think, okay, it's a divisor and it's the biggest one, the greatest common divisor. Why do I have it like this, right? It divides. Well, this just makes it a bit more clear that I want this to be divisible by every other common. It almost seems stronger, but it turns out it's equivalent, right? You can kind of prove that if two numbers are both divisors, then they have to like go into each other somehow if they're common divisors, right? So I could say that for every C, C is less than or equal to D, but I instead want to do it like this, right? And maybe if I want to be specific, I can just say that this is in constant integers, but that's kind of a nitpick. But this is a formal definition of a greatest common divisor, right? It is, I want the divisor to be a common divisor. And then for any other common divisor, right? So this kind of is the definition for what it means to be a common divisor. So this is that D is a common divisor. This part says for all common divisors C, those common divisors all divide into D. Right. And so if we have like A equals 8 and B equals to 16, right? I can find all the common divisors, right? I've got 8, I've got 4, I've got -4, all these things. And then what's the biggest one? The biggest one will be 8. Right, and you can prove this using this definition. Okay? And I'm about to give you another definition, and you can almost, some of you might already guess what's coming up. What do you always talk about, you know, when you talk about greatest common divisors, there's kind of a opposite, right? Instead of a greatest common divisor, you can say that there's a least common multiple, right? So letting A and B be integers, the least common multiple of A and B. Then you might guess this is the LCM is an integer plus such that I'll use two things again. And you'll see that this is almost the exact same thing, right? I want it to be a multiple, a common multiple of A and B. So I'll have that A divides M and B divides M. Right, and by the way, M for multiple, B for divisor, right? You can see why I use these. It doesn't matter what letter I use, but I'm tending to use standard letters, right? You'll see this in other books, right? C for common divisor, D, because it's a, you know, we say D for divisor, but like we usually use D for greatest common divisor. So no matter what letters you're using, even if you're using M or N for your integers, you'll still usually see people say D equals GCDM, right? And you see M equals LCM, right? Just for multiple and divisor. So these are just conventions. You don't have to follow them, but it's typically known that that's what they're talking about. So this says that M is a common multiple of A to B. right? And so just like the other case, we want it to be the least one, the smallest one. And instead of using less than or greater than, we're going to use divides, right? And so for every, let's call it, M, C, I'll use C as well. For every C and Z, A divides C, and B divides C, we have that M divides C. Right, this has to be the smallest one. It has to go into all other common multiples. So these are two definitions for least common multiple and greatest common multiple. I'm sorry, greatest common divisor and least common multiple, right? So now we've formally defined things that you already know. And this is part of what mathematics is. We have to make sure we have a formal definition for everything, right? Even if it's something that seems obvious, well, it's only obvious because someone told you what to use it for or how to use it, but you still need to actually have a definition for this, right? So here's our definitions. And so I want to give you these things so that we can work with them later. Okay? Right. So now we're ready to jump into a couple other proofs. Maybe I'll start with one that just uses divisors. So I claim A divides B and A divides C, sorry, and B divides C, then A divides C. In other words, I want to show that in some way the divisibility is transitive, right? If this goes into this and this goes into this, then this goes into this. It seems obvious, and it should be, right? But we still want to be able to prove it. And this is slowly going to come build up the whole idea of even if it's obvious, you should prove it, because later on, there are some things that might seem obvious, but when you try to prove it, something fails and you don't quite have enough in terms of your conditions, right? So this is why we use mathematics in the way that we do. We want to make sure we conclusively prove everything instead of just claiming it's obvious, right? So again, let's write a proof, but let's go through what we need, right? So we want to start with our premise, and maybe I'll write this over here instead to kind of like, so that I can write a bit more and show you guys the structure, right? So this thing, these are my premises. This is what I start with. And this is my conclusion. Right? So when I start my proof, I can say suppose A divides B and B divides C. That's what I start with. Right? That's what I'm given. Right? So this implies this. So at the end, I should have something like therefore or thus A divides C. That should be what I end with. Right? And just like last time, let's write out the definition. Right? There's a definition for A divides B. There's a definition for B divides C. Right? So each of those has an integer associated with it. Right? So let's pick two letters. I'm going to pick M and N. There exists Mn integers. Follow these two. So I have B equals to AM and C equals to B. Right? That's what it means for A to divide B. There exists an integer such that this is true. And that's what it means for B to divide C. There exists an integer for this to be true. Right? And then we can stop there because we have a definition here, right? So that means we need C to be equal to some KA, right? Where K is an integer, right? And maybe I can say so, because whatever, you kind of see that whatever logic you have, you kind of state, so we have this, right? Because once we have this, by definition, A divides C. So you can even say this here. by definition, right, to finish the proof. So we kind of want this to come from here, and now we can start putting them together, right? Because I want to write C in terms of A, right? So I can almost write C equals Bn, but I also know what B is, right? It's AMN, right? This is equal to A times Mn, right? I haven't told you that these things are associative or commutative or whatever, but for now, since again, we know basic properties of integers, we'll just kind of assume that's true, right? Equals to Mn times A, right? And we'll note that Mn is an integer. Why? Because we picked Mn to be integers that satisfy this statement, right? That exist integers Mn, and since M and N are each integers, their product is also an integer, right? So now I can say let K equals to Mn, right? Then I have C equals to Ka, right? So maybe I can just change this so grammatically to then we have C equals to Ka, and so A divides C by definition, right? And maybe I can even be specific and say this, I picked an integer. So this is a full proof of this statement, right? And you can kind of see the structure. I'm not just going to start from the beginning and just write my proof and be done. I kind of have a structure to how I think about the proof, right? I started from here. I went, okay, I'm not going to go anywhere yet. I'm going to say what I need to end with first, right? I need to end with something over here. And then let's do all the stuff in between, right? So this is another direct proof, but this is another way you want in which you want to kind of think of how to do this, these sorts of things. All right. All right, so let's look at another one. Say that any integer x squared plus 3x plus 4 is and so if we try to do this directly without any other tricks, we might run into some problems because if you don't know what x is, it's just an arbitrary integer. How can I always break this down into 2 times something or 2 times something plus 1, right? But we know what happens, right? We've seen what to show or how to show that if x is either even or odd, we can write it in a certain way and show that something to do with x is even or odd, right? So this is what we would do. We'll call this proof by cases, and this is a standard technique, right? I'm going to split this into cases. We talked about how any integer can be either even or odd, right? The proof will start with let x be an integer. And notice what I'm doing here is I'm responding to this quantifier, right? I'm responding to the for all, right? By saying let x be an arbitrary integer, right? And say that then we know that x is either even or odd. You can check both of these. Case 1. Let x be even. Right. So if x is even, what happens? We can have a definition. There exists k that x equals to 2k. Right? So then we'll go on in the standard way. We'll write this x squared plus 3x plus 4 equals to 2k squared plus 3 times 2k plus 4. And notice what I'm doing here is I'm just saying I don't know how to deal with x, but now that x is 2 times something, maybe that'll help. Let me put this 2k into everything here and see what I get, right? 4k squared plus 6k plus 4 equals 2 times 2k squared plus 3k plus 2. Notice that this is an integer, right? So we can say that let m equals to 2k squared plus 3k plus 2, which is an integer, right? Again, by closure under addition and multiplication. If you were writing this in an actual proof, it might be good to have parentheses and say why this is an integer. It's an integer because the integers are closed under addition and multiplication, right? So let m be equal to this, then x squared plus 3x plus 4 equals to 2m, where m is an integer. So by definition, this is even. So I've showed that this thing is even, but I had to just assume that x was even in the first place, right? So I need the other case. So case 2, x is odd, so let x be odd. And we'll do the exact same thing, right? There exists a k. And here I use k because it's kind of like a different proof. If you want, I'll go ahead and use a different letter here, just to be clear. But it turns out, it's fine. It's fine either way, right? Because I'm starting a new proof. It's not that it's this same k. But again, like I said before, if you want to be absolutely clear, if you want there to be no disambiguity, then you can just choose a different letter just to make sure that you know it's a different letter, right? So maybe instead of k, let's use maybe h. I don't know, it doesn't really matter, right? Let h be in z such that x equals to 2h plus 1, right? So then x squared plus 3x 4 equals to 2h plus 1 squared plus 3 times 2h plus 1 plus 4. And just do some algebra and expand this out. I trust that you guys know how to do that. I'm going to combine everything, so I get 4h squared plus 10h. And what I'm going to do here is I'm already going to notice that this is even, right? But if it were odd, leave out the plus 1. If you know it's going to be odd, leave out the plus 1 so you make your life easier. So you don't have to like get the final solution and then bring out the plus 1 and you're kind of like repeating a step, right? So if you want to be odd, leave the 1 out. But here it's not going to be. It's this. This is 2 times 2h squared plus 5h 4. So now let n, again, I'm picking a different letter, equals to this thing, which because h is an integer, we know that this is an integer by closure of the integers under multiplication and addition, right? Then x squared plus x plus 4 equals to 2m for an integer n. So x squared plus 3x plus 4 even. Right. By the way, notice one thing I've been doing here is when I'm writing out a series of equalities or even inequalities later on, I line up my equalities like that, right? And I choose this so that it's a bit, you're not just like you're not just reading across a line. It's a bit more organized. And two, another reason is this means that for every line, I can justify why that's true. In this case, I didn't need any justification because this is very obvious stuff, right? This is just basic algebra. But for later proofs, and you'll see this when we get to the real analysis section, when we need to really justify each of our steps, and each of the steps might take more explanation, we want to write it in this way so that, okay, we can maybe write this line and then have parentheses on the other side that tell us, okay, this is why this is true, and then we can go to the next one, and that kind of organizes your argument a little bit better. And I'll mention this again when we get there, but this is one standard thing to do just for better organization. In LaTeX, for those of you who want to write something like this is the align environment. I can do a line star to not have the equation at the end. Align is a math mode environment. In other words, you don't need to use dollar signs inside your align environment. There already are dollar signs. So when I would write this, I would have something like this. And I will put an ampersand and an equal sign, right, next to each other. The ampersand says that, okay, the thing that I'm lining up is this equal sign. So I'll write whatever I want here, and then even if I start this over here, even though it doesn't look like it's aligned on the page, the align environment will look for all the ampersands and it will line them up, right? It'll take all the ampersands and put them together in one spot, right? And that's how you get that. So this is just a good organizational technique. I'm not going to write it out because I'm very lazy, but technically this is enough because I've shown that in both these cases, what I want is even, right? But if you want to be really clear, you can end by you can just conclude this, right? You can just say that, okay, thus we have exhausted all possible cases for x being an integer. And so since x squared plus 3x plus 4 is even in all these cases, we must have that for all x in the integers, x squared plus 3x plus 4 is even. You can kind of say all of that. And sometimes this is a good thing to do, right? Even if you've shown everything that you wanted to show in symbols, right? It's good to end with a paragraph of thus because of blah, blah, blah. The statement we want to prove, the statement that we wanted to prove is true, right? Just to be clear that you are done. Because sometimes it's not clear. There are some textbooks that like to stop at a place, and it might not be the end of the proof, but the author will think that the rest of the proof is trivial or super, super easy to see, so they'll just stop there, right? So sometimes and that's fine to do at, once you've done enough math, but I just like kind of saying, be as clear as you can, right? Make absolutely clear to your reader that you're done. All right? Okay. So that's a proof by cases, right? It's still a direct proof. I'm not flipping anything. I'm not doing anything differently. I'm still directly proving that x squared plus 3x plus 4 is even, but I'm doing it through exhaustive cases, right? Some people will call this a proof by exhaustive cases, but if you say proof by case, most people say proof by cases, right? It's known that if you have to prove something by cases, you have to consider every single possible case, right? So that's fine. Okay. So we're all good there. We'll move on. And I'll give you guys more practice in the homeworks. I'll probably split the next few homeworks up into direct. I'll probably have, let's see. I'll probably have one homework on direct proofs, one homework on proofs by contraposition and contradiction, and then a third homework on all of them together, right? Where I don't tell you what to use, and you just kind of choose what you feel like is the best option. So we'll start with proof by contraposition or proof by contrapositive, right? I use the term contraposition just because I think linguistically it's better. But if you say proof by contrapositive, that's still fine. So as a reminder, what do we call this? We call this the conditional statement, right? And we said that the contrapositive is not Q implies not P. And these two statements are equivalent, logically equivalent, right? We've said this. It's not, the converse is usually not true, where the converse being Q implies P. That's generally not true. But if we say the contrapositive, this is going to be a true statement, right? And so this just happens because I want to prove this, but maybe this isn't so obvious, so I'm going to flip it and then prove this. And then you prove this directly, right? Using a direct proof. So here's an example. If a squared is even, then a is even. Oh, and by the way, I should note something here. Notice I'm not saying that, oh, a in the integers is even, right? Why not? Why am I not specifying where it lives? Well, this is because that's already in the definition, right? To be even, what's part of the definition of an even thing, right? We say integers are even. We don't say the real numbers are even. They have to be integers, right? So the fact that a is even and a squared is even is kind of built into the definition inside here, right? So, sorry, I mean that the fact that a is an integer and a squared is an integer is built into the word even here, right? So if you look at this, you might kind of get stuck if you try to do this directly, right? So it's kind of weird because you can be like, okay, if a squared is even, that means a squared is equal to 2k. But then how do I show that a is even? You can do it. It takes a little bit of finesse, right? So let me do this directly first, right? So let's call this P, and let's call this Q, right? So if I want to do it directly, I have to say something like, okay, in other words, P implies Q. So suppose a squared is even, right? Then there exists a k in integers such that a squared is equal to 2k, right? And maybe I want to say that this is equal to something times something, right? Something times itself, because that's what it means to be squared, right? It's multiplied by itself. But then you have to use something about prime numbers here. And I haven't defined prime numbers. Maybe I'll do it next time. But you can just follow along with the logic here. If you use prime number, you can say, okay, if I am divisible by 2, I have to also be divisible by 2 when I go one step forward, right? So it's almost like, okay, if I have to be divisible by 2, I have to be divisible by 4, and so on and so forth. When we talk about prime numbers, we'll talk about something called the fundamental theorem of arithmetic, right? You back in high school, even before that, you did like division shoots, right? You took a number and you kept dividing it up until you get to just prime numbers, and you kind of divide a bit. And you can kind of think of this as if you do a square number and you do this division process, you end up with pairs, right? So this means that when I do this as a pair, there's no way for 2 to only show up once, right? It has to show up twice. So maybe I can say that this is equal to 2 times 2 times m, k equals to 2m, right? So something like that. But then we also know that when we split this up, one of the 2's has to go with one of the a's and the other 2 has to go with the other of the a's, right? So then you'd say that this implies that a is equal to 2 times some n, right? Where n squared is equal to m, right? And so a is even. Notice that this is a correct proof. But not only did you need more mechanics, right? You needed stuff about prime numbers, you need stuff about the fundamental theorem of arithmetic, you need some logic to kind of piece together the idea that, oh, if it divides into 2, it has to divide into 4, then I can move something out. There seems to be a lot of moving parts here. So even though this is a correct proof, it might not have been obvious. And so what happens if we look at the proof again, but we look at the contrapositive? Because whenever I think about trying to prove something and it's conditional, I think which of the sides is easier to work with. Because if we look at the right side, the Q, I know what to do if I already know A is even, or A is not even, or so on and so forth, right? So not Q is a statement that A is not even. But we already talked about parity, right? Every integer is either even or odd. So A is odd, right? So if that's my premise, let me just start my proof. Let A be odd, right? Then what's the definition of being odd? There exists a K such that A equals to 2K plus 1. But then what's A squared? A squared equals 2K plus 1 squared equals to 4K squared plus 4K plus 1 equals to 2 times 2K squared plus 2K plus 1. Right, this is an integer. So you've gotten the idea, but this point I'm not going to write up the super specifics. You know how to say that this whole idea means that a squared is odd, right? And so since a squared is odd, I can say so a squared is not even, right? And that's what not p is, right? If p is a squared is even, then not p is a squared is not even, which is what we've shown. Notice how much easier this was, right? If I know something about the second statement, the conclusion, right, just negate that and show that the premise is false. This is much, much easier to prove, especially in this case, than proving the forward direction, right? So don't always be stuck with trying to prove the forward direction. Sometimes the contrapositive is way easier. There's a lot of cases of this where it's doable, right? You can do it directly, but as soon as you flip it around, it becomes way, way, way easier, right? And one of the ways, in terms of problem solving, this is just something you want to get used to, right? As soon as you see a problem, you want to think to yourself, okay, if you don't immediately see which way is easier, can you kind of think of it, what do you want to work with? And sometimes if you're doing a direct proof and you can't quite get what you want to get, flip it and see what happens, right? Try the contrapositive, right? So for the direct and contrapositive, they're both things you want to try because they're essentially both direct proofs. It's just restating the theorem and saying, what do I want to prove? What is an easy way of doing this, right? So when I have something that's in terms of A, right, and then A at the end, it's almost easier to start with A being even or odd because we have an immediate definition for that we can plug in. Whereas going backwards, it's not so much plugging in, right? There's no such thing as a square root. There's no such thing as dividing. So it becomes way harder to come up with arguments concerning that, right? Does that sort of make sense? So that's kind of what we have there. So whenever we have something, what did I want to say? Right. So whenever we have something along these lines, you want to be sure that you're not putting in too much effort, right? When you are checking to see how you want to prove something, if something feels like it's taking too much effort, maybe there's an easier way. It's not that you're doing it the wrong way. There just might be an easier way to do it, right? So that's what a proof by contraposition is. I don't have too much else to say about this because it really is just direct proof, right? The whole technique is flip it to the contrapositive and see the direct proof is easier that way than the other way. So it's not really a different proof technique. It's the exact same way we prove things as we did before. It's just that one direction might be easier than the other. Okay. Now, I think the last thing we do for today is proof by contradiction, right? And I think that'll be a good place to stop. So let's do a proof by contradiction. And you remember that the way we do this is if we have P implies Q, right? We can assume, so if you want to prove P implies Q, we assume P and not Q, right? Because this is the one case where our truth table was false for this. So if we assume this, so something goes horribly wrong, so its negation must be true. Right, which implies that P implies Q is true. Right? Because these are logically equivalent. I can even say that, right? So that's how I do proof by contradiction. I assume the premise, I assume the negation of a conclusion shows something goes wrong, and so that my original statement had to be true by negation. So let's do the same thing, right? We've done this by direct proof. We've done this by a proof by contrapositive. Let's now do it by contradiction, right? So we want to say P and not Q, right? So I can start with suppose A squared is even, which is fine, right? Because that's what we're given. And then I can say that suppose, for the sake of contradiction, right? And again, remember that I say this to make it clear that that's what I'm doing. I don't want to confuse my readers, right? I want to make it clear that I'm going to assume this and then show that something is wrong, so that as the reader goes along, they know that they are expecting to see something wrong. so that when you do write something incorrect, they're not going to try to track backwards and go, oh, when did we go wrong, right? We know that this is what we expect to happen. So obviously you don't have to do this, but I'm almost going to require you guys to do it. If you guys are turning in a proof, I want it to be written well. And so for proofs by contradiction, I want to see you have it written somewhere. What is the contradiction, right? What is the thing that you're assuming that you think will provide a contradiction? Because this is not the contradictory part, right? This is just our premise. We want that. It's assuming not Q, that's where our contradiction comes, right? For the sake of contradiction, suppose that this is also, the negation of this is also true at the same time, right? So A is not even, or I can even say that A is odd. I can just directly say that, right? That's fine. If you negate A is even as A is odd, that's perfectly fine. Obviously, that's not how we do negation. Negation just adds the word not, right? So like the opposite of black is not white, the opposite of black is not black, right? That's how we do negation. But for this specific case, since we know about the parity of integers, I'll allow you to say that the negation of a number being even is the number being odd, right? That's fine. If you want to be super clear and just say A is not even, and write another line saying therefore A is odd, that's technically even better, right? So that's more correct. Well, I don't want you to say more correct. That's more concise and complete, but I will require you to do that just for the sake of convenience, right? So we have A is odd and A squared is even, but so there exists K in integers such that A equals to 2K plus 1, right? But then A squared, I'm not going to go through the same calculation, right? You already know what to do here. We've done it before a few times. We have that A squared is now 2 times something plus 1. A squared is odd. So from A being odd, we get that A squared is odd. But we also have, from the premise, A squared is even. This is not possible, right? So I can say this, so A squared is both even and odd. That's obviously not possible. We've said that any integer has to be either even or odd, not both. But here we've proven that it's both. So something had to be wrong. And what was the only thing we assumed that could have been wrong? It was this statement, right? So here we say that, but we also have that A squared is even. So A squared is both even and odd. I'd usually say this is obviously false, right? Or just this is false. So we have a contradiction, right? And usually when you're proving a proof by contradiction, right, the format is at some point, say for the sake of contradiction, do your stuff. And once something goes wrong, you just say we have a contradiction. And once you've said that we have contradiction, you can say that our assumption, or I should say, thus our assumption that A squared, A is odd, or A is not even, is false. So A is even. And there's our proof, right? We've proven that A is even because we showed that not Q is not possible, right? So that's how we do a proof by contradiction. So you've now seen 3 different ways to prove this thing, right? Now, there technically could be a 4th way, right? We saw proof by cases. We can even try this using A being odd and A being even and see if the odd one doesn't work, then A has to be even, right? Well, that's sort of like part of the proof by contraposition, and it's sort of part of the direct proof, right? So it's not wrong to do that, but it's more clean to do one of these 3 methods, right? Either directly using prime factorization, by contraposition using something about A to show something about A squared, or contradiction to show that if both of those, if P is true and Q is not true at the same time, then something goes wrong, right? So you've seen how versatile some of these statements can be and some of these truths can be. It doesn't matter how you do it. They're not like between contraposition and contradiction. They're pretty much, we did the same thing, right? Notice in the proof by contraposition, if you go back in your notes, we did the exact same computation as in the contradiction. It's almost the same. It's just which one do you prefer? I personally would have preferred the contrapositive because it's almost immediate to see that if I know this is not true, then this is not true, right? But that's not to say this is wrong either. So the big thing I wanted to say here is really just that prove it however you want, but choose what's easiest for you. Now, it's sometimes, I think I mentioned this before, but I want to reiterate it. A proof by contradiction is sometimes, how do I say this? It's sometimes not the way to go. And what I mean by that is typically you will have issues proving something by contradiction if it's not meant to be proved by contradiction. So I will try to, so whenever I want you to prove something like contradiction, even though I didn't tell you it's contradiction, I will try to make it so that it's something you've seen me prove by contradiction before, or it's something you've proven by contradiction before, but you should always try direct and contrapositive proofs before contradiction. Contradiction should be your last resort because sometimes the arguments in contradiction can get a bit convoluted. Okay, so before we end this, there's one last example I wanted to give for a proof by contradiction, right? And this is a very standard thing. Square root of 2 is irrational. And this is gonna take some of the definitions that we've come up with so far to get this, right? In other words, irrational being not rational and so on and so forth. And assume we know what square root of 2 is, right? Assume it's a number such that, assume this is a number x such that x squared is 2, right? Even though we haven't defined the square, we will assume that that's how we get this. If you pause the video and kind of go back, or for those of you in class, if you want to just close your ears and close your eyes and not look at what I'm about to prove, you can try to prove this. It's not going to be very easy, especially if you haven't seen something like this before, right? If this is your first time seeing this, you're going to be kind of stuck, and it's not going to be obvious what to do, right? And so what I'm trying to do with this is there are some times when I might have to show you what's a standard, especially if you're starting off in mathematics, you want to kind of see what is the standard way to do things. And then as you do more and more of these, you kind of develop your techniques and you start seeing what makes sense and what doesn't make sense, right? What should I try? What should my first steps be? And so on and so forth. When I do this, you're going to see that, you're going to be able to follow along the proof, right? It's not going to be hard to follow along. But at the same time, you have to be honest with yourself and ask yourself, would I have come up with this on my own? And if the answer is no, that's okay. But the important thing isn't to say yes to that question. The important thing is, can I build up an idea of how someone would have come up with this? Okay? So, I'm going to do this by contradiction. Because usually when you say something is not something, right, you have a definition, especially because I don't have a definition for what it means to be irrational, right, other than it's not rational, usually that means it's a proof by contradiction, right? The only way I can say is suppose it's this other thing and show something wrong. Show that it can't be the opposite. So I would say suppose, for the sake of contradiction, and right, notice I'm saying this at the start. Suppose for the sake of contradiction that square root of 2 is rational. We define irrational, right? What does it mean to be rational? That means there exists A and B as integers A and B, such that their greatest common divisor is 1. So now that we've talked about the formal definition of the greatest common divisor, we can use this, right? And remember that when I gave you the definition of rationals, I just kind of wrote this down, assuming that you guys know vaguely what a GCD is, right? That's fine. But now we have a formal definition for this, right? Such that GCD of A B equals 1, and A over B equals to square root of 2, right? Well, let's do the standard thing we would do in algebra. We then have that a squared over b squared is 2. We write square both sides. This implies that a squared equals to 2b squared. But wait, b is an integer, b squared is an integer, a squared is 2 times something, right? So a squared is even. But wait, what was that previous theorem that we proved in like 4 different ways? We said that if a squared is even, then a is even, right? If we haven't done that yet, then maybe you can do that here, right? Maybe this is where you would have a lemma, right? So now that you're seeing this, maybe what we had before can be written as a lemma. We have a lemma that says if a squared is even, then a is even. Then now in the process of you proving this theorem, we would invoke this lemma and say, okay, by the lemma, since a squared is even, we then have that a is even, right? But then what does it mean that a is even? So this means there exists a in integers such that a equals to k, right? But then a squared is equal to 4k squared, which is equal to 2b squared, right? Because look, I have a squared equals 2b squared. So a squared is the same as this. If I want to be really specific, I'll write it backwards, right? I start with 2b squared. This is equal to a squared, which is in turn equal to 2k squared, which is equal to 4k squared, right? If I want to be really specific, I can write it this way. But what does this mean? This means b squared is equal to 2k squared. But by this same logic, this means that b squared is even, which implies that b is even. But wait, let's look at something here. Thus, what does it mean to be even? Well, another way to write it is 2 divides a and 2 divides b, right? Now we have to use this condition. And a lot of times this is how this is going to work. When you're going through a proof, pretty much all the time, you're going to use every single condition given to you. And if there's one condition you haven't used yet, you might be stuck, right? Now, obviously, in a research level, you might not need every single condition in the world, but typically when you're given something to prove, especially in this level, you will use all conditions. And if you haven't used all conditions and you're stuck, maybe look at the thing you haven't used yet. So here we haven't done anything with the fact that the GCD of A and B is equal to 1. So I'll say that since the GCD of A and B is equal to 1, and 2, by definition, is a common divisor, we thus have 2 divides 1. This is obviously false. Or clearly false. Right, and you can see why, right? Like, it's almost like I'm taking 1 divided by 2. Well, we don't know what division is, but you can think of it that way, right? This means that there exists an integer such that 1 is equal to 2 times that integer. But if you take 2 times any integer, that's even. But 1 is odd. There's no way 2 is going to divide 1. Thus, we have a contradiction. And sometimes what I'll say here is, thus, we have a contradiction, and so our initial assumption must be false. But in this case, you can just write, since our initial assumption was that root 2 is rational, so root 2 is not rational, and thus we have proven that the square root of 2 is irrational, right? Just one more thing I want to say about this. This goes back to the whole definition thing, right? Because I could have said that, oh, 2 is a common divisor, but it's not the greatest one because 2 is bigger than 1, right? But that's not the definition that we use. It's equivalent, but it's not the definition. We have a set of proposition that says that, right? So we want to follow the definition and say, okay, we use this, and there's a contradiction here. You could have done this another way, right? You could have said that, oh, 2 divides A and 2 divides B, therefore, the greatest common divisor must divide 2. Sorry, must be a multiple of 2. but 1 is not a multiple of 2, so the GCD of A and B is not equal to 1. And then there's your contradiction. That's fine as well. That's still a contradiction, right? It doesn't matter if you assume all the conditions are true and show something's false, or you assume everything else and show that one of the conditions is false. Both of those are the same thing, right? It's just how you would prefer to write it, right? So either way, you will get a contradiction somehow. And this is the this is the standard proof of showing that the square root of 2 is irrational, right? That's a very, very, very standard thing to do. And so you can see that maybe in here, this is the thing that required another proof inside of it, right? And we've already proven it before, but maybe I'll ask you like on a homework to prove that the square root of 3 is irrational. And then you'll do the exact same process and you get to here and you go, wait, I don't have even or odd, I now have divisibility by 3, right? So maybe to cover that case, I'll say this, we have even as 2k or 2k plus 1, right? That's all we have. Here's a trick also to do something by cases, right? If I want to show that something is divisible by 3 or whatever, or if I'm saying that if it's not divisible by 3, one of the options, keep in mind that I can have this, right? Something like 2k, sorry, 3k is something divisible by 3. And then I also have numbers of the form 3k plus 1, 3k. Right. Whatever I multiply this k by, I have that many ways I can write a number, right? And so I can write a number in any of these ways. So if you're talking about any divisibility, right? If I'm saying that, okay, if some number is divisible by 3, then this other thing is divisible by 3, and you want to do it by cases, these are your 3 cases, right? So we can extend, so when we say even or odd, it's divisibility by 2. So there's 2 options, odd or even. That's why we paired it. Either it's 2k, where it's even, or it's 2k plus 1, where it's odd. Here, I'm not calling it even or odd, I just have that many cases. If I'm showing divisibility by 3, I have 3 cases. If I have divisibility by 5, I have 5 cases, and so on and so forth, right? So we can talk, if you want me to talk about this a bit more, we can. Shoot me an email if you want me to go more into this concept. But we'll revisit this concept in number theory when we're talking about, actually, no, even better, we'll do this soon. After this once we're finished with this unit, which I think we should be done soon, I'll start talking about functions and equivalence classes. And when we start talking about equivalence classes, I'll talk about this a bit more, right? So we've seen a proof by, let's see, we've seen a proof by direct proofs. We've seen a proof by contraposition. We've seen proof by contradiction. So like I said, I'll give you homeworks on, sections where I say, okay, do this by this method, right? And then afterwards, I'll say, prove this using any method. And I kind of want to see what you would choose. And if you want to do it by multiple methods and see if you can do it multiple ways, by all means do it, right? So when you turn in your homework, or if you're going to turn in your homework on, like, say, the section of proof by contraposition, feel free to try them by contradiction or direct proofs and see if you can do it, right? The thing you turn in should be the proof by contrapositive, but if you think you should be able to do it another way, but you're not sure how, let me know. And I can see if there is a way to do it like that, or if there is a standard way to do it like that, and we can, see how to help you figure that out. Any questions? Okay, so I think that's a good stopping point for today. I'll talk about biconditional proofs a little bit on Friday. I'm not sure what else. I'll kind of look through some of the material I have and see like if there's anything about this section. So basically these are like introductory proofs, right? So these are the first kind of proofs you'll see how to do. I want to see if there's anything else I want to cover, but if not, Friday will probably be a shorter lecture where I just give you more examples. But that's going to be it for sections 1 and 2. And after that, I'll give you guys your take-home test, which will kind of have all the stuff from these sections. And then after that, we're going to start diving into less of a proof-based thing and less introductory proof thing, and more of a, here are some things you need to know, right? We'll launch into more definitions, right? We'll start talking about different definitions. We'll start talking about how to think about, more difficult definitions. and then we'll start using that as a springboard to start talking about more areas of mathematics, right? So the next thing I'll do in section 3 is section 3 will be on functions, right? I'll talk about functions, types of functions, what we can do with functions. And then once we're done with functions, that means that I can then start talking about, say, algebra, right? I haven't decided what order I want to do the various topics in, but I think I will start with probably abstract algebra or real analysis, one of those two, and then we'll see where to go from there. Okay? And I will see you guys on Friday.